Good evening, everyone. We're Team Retrofier, and we're a team of three. The idea behind our project is retrosynthetic analysis. During the drug development process, after a candidate has been identified as a potential drug, satisfying all necessary properties and conditions, the next important step is to manufacture or synthesize it. This requires chemists to determine the synthesis plan. Retrosynthesis or retrosynthetic analysis is one technique for identifying a required synthesis plan for such a candidate molecule. This slide shows some examples of the identified retrosynthetic plans. There are different approaches for solving the retrosynthesis problem. The traditional approach being chemists identifying the best paths manually with the help of their expertise and prior knowledge and by conducting laboratory experiments. And with recent advances in AI, ML, and deep learning, there are computer-aided synthesis plannings that are available, which use the ML techniques to accelerate the planning processes. And one such approach that we found fascinating was modeling this retrosynthetic analysis as a game and using reinforcement learning to play that game by defining some rules and plans. Here we show an example of a retrosynthetic game that was played using reinforcement learning, where the bold lines show the path that has been identified, the best path that has been identified for a particular drug. What we identified is that more often than not, the synthesis plans produced manually, even with prior knowledge and expertise, of course, require verification. And this implies automatically that computer-aided approaches too require validating the correctness of the reactions that were identified in the retrosynthetic steps. These computer-aided plannings we identified rely a lot on reference templates for each reaction. A certain researcher called Connor Coley curated manually certain templates based on a few reaction types and using atom mapping principles. This is where we identified common sense reasoning can be used by using those atom mapping principles and implementing them as rules corresponding to the mentioned reaction templates. Using this idea, we defined a few rules and predicates that we thought best fit the roles in the chemical reactions. The grounds for common sense reasoning that we used for implementing this are, we asked ourselves questions like, are the compounds organic? Does the stoichiometry of each reaction change? Is any compound toxic, which would be the basis for disregarding the compound immediately from the plan? And is the target compound that we started with a drug in the first place? And the main constraint for approving a retrosynthetic plan, which is identifying a material that is commercially available to start with. The main while implementing this, we assumed some conditions like we'd use only 2 reactant reactions considering the time constraints and implementation constraints. And also we'd only deal with single step reaction verification. We use some basic rules of chemical reactions. Toxicity was checked against a known list of toxic compounds. Some of the main challenges that we faced were how to represent the molecules after serious consideration, we chose the chemical formulae and represented them using Prolog's dictionary. What fascinated us while doing this project, and in fact, what motivated us to choose this topic, was the immense scope it manifests with respect to interdisciplinary research, collaboration with chemists and informaticians in this field. and the level to which integrations with existing software like OpenBabel, which contains the properties of reaction, is possible. To quickly show a demo of the project that we invented, the rules corresponding to toxicity of a compound and checking if organic compound is present in here and checking if it is a a commercial compound or not are here. So one of the examples that we probably show here. Like mentioned, we represented the molecules in the form of Prolog's dictionary, where atom and its corresponding number of atoms that are present in the molecule are represented. This is satisfied because all the rules that correspond to the reaction have been satisfied. Probably another example could be this is not satisfied because stoichiometry of a reaction has not been satisfied, and one of them is a toxic compound. That's it. Thank you.